Hi, let's finally move into Module 5, the last module. This unit is about statistics. It is one of the longer modules. It covers most of 3 chapters in the textbook. The good news is that it's also, I think, the easiest one. I think you will have seen quite a bit of the material before in some version, and the material that you haven't tends to be pretty easy to pick up, I think. That was deliberately chosen, by the way. I tried to make the course end on an easier note rather than a difficult one. Statistics, of course, is everywhere. You can't pick up a newspaper or watch the evening news or browse very many internet news articles before you see something about some sports statistic or a political poll or some educational statistic. And it's an important life skill to be able to interpret that and filter out things that are important from those that are not. So let's first look at some ways of displaying data. The topic of Chapter 5 is about analyzing data. One way is to generate graphs using that data. Another is to generate what are called statistics or numbers that help summarize the data. The point is to take a large set of raw numbers, raw data numbers, and try to coax out some story behind them. So let's work with this example for a while. Babe Ruth, of course, was one of the most famous baseball players of all time. He started out as a pitcher and then achieved his fame as a batter who hit a lot of home runs, and his single season home run record of 60 stood for a number of decades before it was broken later in the 20th century. Here are Ruth's home run totals per season for the years 1920 to 1934. Let's use this data to generate a histogram. I'm going to do it in a very cookbook sort of way. Here are the steps, and you just follow them, and out pops the desired graph. Choose the number of classes, usually between 5 and 15. This is going to eventually end up being the number of bars in the histogram. You don't want too few. The data is summarized too much and you can't see enough detail. You don't want too many. The data is not summarized enough and you get overwhelmed in the detail. I'm going to more or less arbitrarily choose 10. Compute the range, which is the highest data value minus the lowest data value. I look at the list. The largest number is a 60. The smallest number is a 22. And so the range is 38. Notice that the range is a single number. Compute the so-called class width. Take the range and divide it by the number of classes that you want, and then perhaps round that. So my range is 38. I want 10 classes. That's 3.8, and so I'm going to round that up to 4. The meaning of round depends largely on the precision of the data. Here the data themselves were displayed to the nearest integer, so I choose to round up to the nearest integer. But if these had been numbers like 54.3 and 54.9 and 54.6 and 54.7, then to round up to the nearest integer probably would have been silly. You would have lost most of the detail. Next, choose the lower boundary of the first class as the lowest data value. That's what's typically done, or sometimes you can go a little below that. For us, the lowest data value was 22. Repeatedly add the class width to generate the lower boundaries of consecutive classes. So the class width is 4, and so 26, 30, and I'll just go ahead and write them all. And if I added 4 again, I would get up to 62. The highest data value is 60, and so those That's all the lines I will need. Now, as far as the classes themselves, I can do a couple of things here. I can go 22 to 25 and 26 to 29 and so on. That makes sense with integer data like this. In other types of situations, fractional values might be possible, and so you might have a 5.7, for example. And so if you went 22 to 25 and then started at 26, there would be a gap and numbers might fall in the gap. So I'm going to do something a little different, and in most cases it doesn't really matter which convention you choose. This means 22 up to 26 by common assumption or common convention, and 26 up to, but not including, 30. So now the classes have no gaps between them, so there's no question about data values falling in a particular class, or that there be a class for each particular data value. The thing now then, what happens if you get a data value of 26? Which class does it go in? It's pretty standard convention that it goes in the class to the right, or the larger class. Okay, let's take the data next and tally it. So I'm looking at the data list and saying, oh, there's a 54, so that falls right on a class boundary by our convention. That goes in the higher class. There's a 59, that goes in this class, and so on. A 35, a 41, 46, 25, 47, 60, the big number, 54, 46, 49, 46, 41, 34, and 22. And then for readability, we might just say 2, 2, 2, 5, 2, 2. You could write zeros here. Quite often you just leave it blank because it's easier actually to see a blank than it is to see a zero in a list of numbers. Okay, let's take this so-called frequency table and convert the information to a graph, specifically to a histogram. A histogram has two axes, a vertical and a horizontal. The horizontal axis gets the same label and units as the data. So I look back at the raw data and there were numbers like 54, 59, and so on. What were those? Those were numbers of home runs. And on the vertical axis, I could label this vertical axis frequency. It might be a little more instructive to say number of. So it's going to be these numbers, 2, 2, 5, and so on. And the question is 2 what and 5 what? And if you think about it, 2 what? Well, there were 2 numbers in this list that were between 22 and 26, and the numbers, there was 1 number per year or per season. So the frequencies are counting number of seasons. All right. Then let's put scales on these axes. And by the way, as you're drawing these graphs, a completely correct graph must have units and it must have a data scale on it. Otherwise, it's maybe a pretty picture, but it's not really a full-fledged graph. Also, it's a good idea to use as much of the paper as you can. We already talked about that when we were doing other types of graphs. And so I see that the number of home runs, the x-axis variable, goes between 22 and 62. In particular, it doesn't start at 0, and so what's quite often done is a break maybe some squiggly lines like this, and then you can put the 22 right here, and you don't have to waste a lot of space going between 0 and 22 where there's no data going to be anyway. So then 22 to 26, and I'm marking off the class boundaries now. On the vertical axis, the number of seasons goes between, well, 0, there are a number of zeros, up to as many as 5. So there's no real reason that I need to do a scale break on the vertical axis. I'll just put the range between 0 and 5. All right, now we're ready to draw the histogram itself. Between 22 and 26, there were 2 seasons. So draw a bar like this. Between 26 and 30, there were 0. So I don't draw a bar at all, or I can think about drawing a bar of 0 height. Between 30 and 34, also none. Between 34 and 38, there were again 2 seasons, and so on. 2 between 38 and 42, 2 between 42 and none rather between 42 and 46, and then between 46 and 50 there's a jump to 5 seasons, back down to 0, and then 2 and 2. And there is the histogram. Of course, you can also generate such graphs using computer software. One of the things that you use a histogram for is to determine the overall shape of the data, and we'll discuss in a moment why that is an interesting question to talk about. So what I mean by overall shape, if you think about these histogram bars as physically being sticks sticking up out of the ground, say, and then you take a blanket and drape it over those sticks and ask what's the general pattern that the blanket follows. And so you see that it might assume a shape like this. I'm not attempting to follow all of the individual ups and downs, just the overall trend. This is called the envelope of the distribution. And now I can start to say things like, oh, the envelope has a peak here, and the envelope kind of stretches out to the left for quite a ways, whereas the right side is not stretched out as much. Let's give names to those concepts we just identified. One way of classifying the shapes of distributions is the direction of stretching. So symmetric means even somehow, and what we mean here is that there's some place where I could draw a vertical line, and if I thought about this as being a piece of paper and the histogram were cut out, then I could fold across this vertical line and the two halves would align on top of each other pretty well. So there's just as much to the left as to the right in corresponding positions. Whereas here's a situation where the left tail has been stretched out. Skewing means stretching, so left skewed, stretched out to the left, and here's a distribution that's been stretched out to the right. Also, we can talk about the number of peaks that a distribution has. So mode refers to the most commonly occurring value, and non-modal means there is no most commonly occurring value. In other words, there's no peak really here overall. The distribution is relatively flat, whereas here is a graph that clearly has a single main peak, and so that's called unimodal or one mode. And here's a graph that has 2 peaks, a so-called bimodal distribution. Let's look at several examples here, and I'm just asking you to think about the overall shape. We're not even going to attempt to put numbers on these histograms, just to imagine what they might think about. If I were to go to a cereal boxing company or a cereal company, and where they fill cereal boxes and ship them out, and go to look at an assembly line, processing line, where they were filling boxes that were labeled 32 ounces. And I stood at the end of the line and I weighed the cereal boxes coming off one at a time. And I recorded each weight, and then I made a histogram of all those weights, maybe hundreds of them or thousands of them. And I made a histogram in the sense that here was weight in ounces, and here is number of boxes, and say here is the number 32. Then what does the graph look like? Well, first of all, do you think off of this production line you're going to get a box of cereal that weighs 20 ounces? Probably not. The cereal company is in business to do what they say. They don't, and like similarly, you're not going to get a box of cereal that weighs 50 ounces. Two reasons. The cereal company doesn't want to overfill their boxes because that's giving away free food. But in a regulated society, at least like the United States, they don't want to underfill their boxes as well. They might get caught, and there are fines for advertising that you're giving a certain amount of the product when in fact you're not filling your boxes with that much. Baskin-Robbins Ice Cream Company, for example, was fined a few years ago for underfilling their ice cream cups. I don't suppose it was intentional, but they were, and there was a stiff fine levied on them. Okay, so the cereal company has their manufacturing line engineers trying to calibrate their equipment, and so that about 32 ounces goes in each box. But can you get 32 ounces exactly in every box? No. I mean, cereal comes in flakes, and so each flake weighs a discrete amount. You can't have infinitely fine variation in the weight of the cereal boxes. And the calibration equipment is not perfect. But I think that most of the cereal boxes are going to weigh near 32 ounces. A few will weigh a little bit less. A very few will weigh a lot less, and likewise on the upper end. I think what you would get is a distribution that look very much like this. Probably unimodal with a peak near 32, and probably roughly symmetric. There's probably about as much overfilling as underfilling. Do I know that for sure? No, but it's a good guess, and I wanted to illustrate the kind of thinking that goes into situations like this. And so if you stood at the end of the cereal line, as I said, and got a distribution shape that looked very different than this, maybe that was very badly left skewed or right skewed, it would probably be of great interest to the manufacturer to know that, because probably his production equipment was out of calibration. How about heights of American adults? So we do height in, say, inches, and here is number of people. Okay, so 60 inches is 5 feet, and 72 inches is 6 feet, and so on. Might want to think yourself about what this might look like. Here's what I predict. Maybe a roughly symmetric distribution, but perhaps a bimodal one. At least there's some possibility. Why? Well, one of the peaks might be here at about 5.5, 5.6. And another peak I would predict would be here at about 5.10 or so. And what's going on there? Well, these are adults consisting of both men and women. the average height of females is something like 5'5" or 5'6". The average height of males is something like 5'9", 5'10", something like that. And so what's actually probably going on here is there's a group of women who has a distribution shape something like that, and also a group of men whose heights have a distribution shape maybe like this. And when you take these and combine them, you get something like the original red picture. When you see a bimodal distribution, it's quite often, not always, but quite often an indication that maybe there are a couple of groups, multiple groups being mixed in this population. That may be fine, but it also may be an indication that you should think about maybe separating the groups and studying them individually. So maybe it would be more beneficial to study the height of women and the height of men separately rather than studying combined heights, depending on what you are trying to do. That's another reason why you would want to know the shape of a distribution. And how about if I did a graph of income in, say, thousands of dollars, and here is number of families. Well, I think the average income of U.S. families now, not people but families, is somewhere around $50,000. And so what kind of shape? Actually, to draw the graph more accurately, I think I'm going to move my 50 to here. Okay, if 50,000 is the approximately the average value, then it's a good guess that maybe that's about what a lot of people are making. Can you make less than 50,000? Sure. How low can you make? Well, probably all the way down to zero. Some families may not have any income at all if they don't have a wage earner. But decreasing numbers of families would not have that. So I think you would probably see a shape something like this on the way down to 0 from 50. And now how about above? Can you make more than 50? Oh, sure. 100, yes. 200, yes. 300, yes. A million? Yes. 5 million? Yes. 10 million? Yes. 100 million? Yes. A billion? Yes. There are a few people, and a very few people, families who make $1 billion a year. And so what you're going to see almost surely is a graph that looks like this. Let me redraw that just a little bit. It comes down, 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 and gets closer and closer and closer, and never really touches. How far out does this go? Well, on this scale, if that's 50,000 a year and that's 100,000 a year, then someone, a CEO of a large company like Microsoft, could literally be in the next room, or maybe even in the next building or the next county, depending on how high of an income there really could be. A very highly right-skewed distribution. There's a very long, skinny right tail going way out here. And that has some implications when you go to compute an average, for example. We'll talk about that in the next lesson. You often would use a histogram or a graph of the distribution to see if the distribution is badly skewed, and if it is, then there are certain things that you probably don't want to do in your follow-up analysis. Let's look at another type of plot. Here's the same data, Babe Ruth's home run data. I can do something called a stem leaf plot. The stem leaf plot separates the digits of the individual numbers themselves. If I have two-digit data like this, then there really is only one way to separate it, between the 5 and the 4, between the 5 and the 9, between the 3 and the 5, and so on. Then I take the stems and I list them in a vertical stack, a column like this. So the lowest stem that I see is actually a 2. the highest stem that I see is a 6. At any rate, once I get started, I should not skip stems. I should just keep labeling until I reach the highest stem. So 2 through 6 in this case. And then the remaining digit, the second digit in the numbers, is a leaf. And here's how you make this stem leaf plot then. I see a number like 54, so it has stem 5 and leaf 4. 59 has stem 5, leaf 9. 35 has stem 3 and leaf 5, and so on. So 41, 46, 25, 47, 60, 54, 46, 49, 46, 41, 34, and 22. And that's it. A couple of things to point out. One is that the raw data is actually retained here. So for example, now if I cover up the original data and look at the stem leaf plot and say, was there a 37 in the original data set? I can look and see, no, there was not. I ask you, was there a 59 in the original data set? Yes, 50, and the 5 and the 9 are here. I can't do this on the computer screen. If you're taking notes on a piece of paper, you might try taking your paper and rotating it 90 degrees counterclockwise like this. And what you'll see then are the stems going along like this, and then the leaves are stacking up above them. And that's basically a histogram. So a stem leaf plot is really doing the same thing as a histogram. It's just that the spacing, the class width, is controlled by the data itself. In this case, if I take one line per stem, then the automatic spacing is 10. Each jump from one stem to the next corresponds to 10 units of the data. I can also talk about the envelope here. So for this case, the envelope of this data looks something like this. And does the data appear symmetric, left skewed or right skewed? Probably roughly symmetric. Here's another thing you can do with a stem leaf plot. You can make several of them and put them side by side. Another famous name in baseball is Mark McGwire, also known for hitting a lot of home runs. Much later, 1987 to 2001, were his playing seasons, and here was the list of the numbers of home runs that he hit, and most famous now for this number 70, which of course is higher than Babe Ruth's. I am asking to make a back-to-back stem leaf plot of Ruth and McGwire. And so what we're going to do is put the stems in the middle, and then off on one side, say the right side, put the leaves for Ruth, and off on the left side, put the leaves for McGwire. Now, you're going to use the same stems for each, so first let's look and see what stems we'll need. For Ruth, the stems went from 2 to 6. For McGwire, I see stems as low as 0. Notice 9 is 09 as a 2-digit number, and stems as high as 7. So a stem of 0, and then stem of 1, well, you say there aren't any numbers in either data set that start with the digit 1. That's true, but remember, don't skip stems. So we're going to go 0, 1, 2, 3, 4, 5, 6, and 7. Now, let's do the stem leaf plot for Ruth. It's going to be the same thing as we had before. So I'm just going to recopy this stem leaf plot down here. Notice up here I put boxes. The reason for doing that was to force you to line up leaves. If you're going to use this type of graph to identify the shape of the distribution, then the spacing of the stems the spacing of the leaves has to be consistent, so you can see which lines are longest, the lines for which stems are longer than others. So here I don't provide a grid anymore, and so as you're generating the plot, just be sure to keep individual columns of leaves going. So there was a 5 and a 2 in the stem of 2. In the stem for 3 there was a 5 and a 4. In the stem for 4 there was a 1, 6, 7, 6, 9, 6, 1. In the stem for 5 there was a 4, 9, 4. And in the stem for 6 there was a 0. And again, I'm trying to keep columns of leaves lined up. For McGuire, there was a 49, so now I'll put the leaves going off to the left, a 32, a 33, a 39, a 22, a 42, a 9, a 9, 39, 52, 58, 70, 65, 32, and 29. Okay, and now you can start asking questions like, who seems to have the higher home run total? Who was the better hitter, maybe is the question. Looking at this, you see that Ruth's values tend to be in the 40s, and most of McGuire's numbers were actually in the 30s, although there were some higher than that. And so probably Ruth, the graph now allows our eye to pick out the fact that most of the Ruth leaves seem to be on the higher end than McGuire's leaves. The stem leaf plot also picks out something else that's interesting. Here are a pair of 9s, and then there's a gap here. These are called outliers. When you see data values that set apart by themselves, they're not very close to the rest of the data, they're called outliers. And in statistics, outliers can have a lot of effect on your analysis. So if you're computing averages, for example, the outliers are going to be pretty important. And for that reason, you should probably go back and investigate outliers and say, are those numbers really right, or did somebody make a mistake somewhere? So first of all, nobody made a mistake. This really was McGuire's home run total in 93, the 9, and then in 94, again, there was another 9. And you ask, why is that? What happened? Well, if you dig back into the history of baseball, I forget which was which, but in one of these two numbers there was actually a lockout or a strike, and so the baseball season was shortened, and so no wonder Mark McGuire only hit 9 home runs. He didn't have very many at-bats that season. And then in the other year, he was actually injured fairly early in the season, and again didn't get very many at-bats. So of course, if somebody isn't getting a chance to bat, they're not going to hit very many home runs. Now, if we're talking about an average, how many home runs did Mark McGuire hit during a season on average? The question becomes, should you leave these 9s in here or take them out? They're going to lower his average, of course. Should you penalize a player in terms of statistics for just being unlucky to get caught in a baseball strike? Or should you penalize a player for being injured? It's maybe easier to argue that the injury number should be kept in rather than the strike number, but still, those are decisions to be made, and they're decisions that can't be made by just a mathematician or a statistician. They have to be made by the user of the data. You have to have a goal in mind for doing this analysis and decide that because of what I'm trying to do, I choose to keep the 9s in, or I choose to take them out, or maybe I'll keep one and throw the other out. Point is, though, that you need to analyze outliers and investigate whether there are errors involved and they should be taken out, or whether they're legitimate data and should be left in. And we'll stop there.